I am Shreyansh. I am presenting on work on Federated Learning for commercial image sources. Federated Learning is a collaborative machine learning technique in which multiple clients can collaborate together to jointly learn a global model without exchanging sensitive private data. Federated Learning was proposed by Google in the year 2017. Now discussing the limitation of prior work, Fed average has two major limitations. Fed average can have convergence issue if the data is non-identically distributed among the clients. Also, Fed average trains a global model to fit an average client, and therefore it does not generalize well for a client with local distribution that is very different from the global distribution. Also, most of the previous work in the field of computer vision applied federated technique on a single dataset artificially divided among the clients, which is far from the real world scenario. Inspired by these challenges and problems, we make the following contribution. We create a real world dataset by collecting images from commercial image sources to study application of federated learning in the field of computer vision. In real world setup, we propose Fed-Cyclic algorithm, which is robust to statistical heterogeneity among the clients. We propose Fed-Star, which provides better personalization capabilities to the global model. Moving on to a proposed dataset, our dataset is inspired by Office 31 and contains objects found in the Office settings. It is a dataset which is designed for the purpose of image classification. Our dataset is collected from 8 different clients, representing 8. Our dataset is collected from 8 different commercial image sources, representing 8 different clients, and has same 31 categories as in Office 31, with more than 23,000 images. More information about our dataset can be found in our paper. Now, moving on to proposed method Fed-Cyclic. It is a simple to implement algorithm in which a single model is rotated across a client in a cyclic fashion. So a client receives model from the previous client, it trains the model on its local set and transfers the updated model to the next client in a cyclic fashion. So in this equation, we can see that once the client K is trained and updated, it transfers its weight to the next client for its training. So our algorithm is computationally inexpensive as a parameter of only one client is passed to the next at any given time. Our algorithm is robust to statistical heterogeneity as every client gets a fair opportunity to train global model on its local data. And while being simple to implement, it attains higher accuracy and creates better personalized global model than our baselines. Now moving on to the next proposed method Fed-Star. So once the local clients train the model on its local data, instead of going for the global aggregation as in Fed average, we perform pre-aggregation among local clients for a fixed number of periods, in which every client receives model parameters from every other client in star topology-like manner. In pre-aggregation, each client prioritizes learning of outlier feature by testing others' model on its own local dataset and giving more importance to client that has significantly different feature than its own to better capture the outlier feature. Once the pre-aggregation is performed for a fixed number of times, we go for a global aggregation, in which global model is formed by aggregating the local pre-aggregated models. Due to our smarter pre-aggregation, our global model has better personalization capabilities. So the pre-aggregation steps can be better explained by the following equations. So in the first equation shows the calculation of a matrix, weightage matrix for the client K. So in this, a client K receives model update from all the clients in the network and evaluate the accuracy of each model parameters on its local dataset and give more weightage to the client with lower accuracy so as to better capture the feature, so as to better capture the outlier feature that is present in the network. These weights are then normalized for the updation of the weight of client K as shown in the equation 2. So Fed-Star attains higher accuracy than the baseline, and the Fed algorithm trains a model that trains the global model that has better personalization capabilities. So we perform the task of image classification on a dataset and evaluates the result on the accuracy matrix. We can see that Fed-Cyclic and Fed-Star attains more than 1.5% in accuracy over the baselines when evaluated on our own dataset. Moreover, to better understand the personalization learning of our model, Fed-Star outperforms all the local model trained using traditional machine learning methods in the baselines. Fed-Cyclic also outperforms all of the baselines in 6 out of 8 cases, showing better personalization.